In the previous class, we discussed about the formation of Newton's rings and the experimental arrangement also. So, how to get the Newton's rings pattern. Here we are going to discuss the real interference which is happening inside the glass plate and planar convex lens arrangement. So here you can see the arrangement which consists of a planar convex lens which is represented as APB and a plain glass plate in this yellow color. Okay, so here we have a planar convex lens APB, and I'm representing this glass plate as XY. Okay, XY is my glass plate. So we have a planar convex lens which is placed on a glass plate. Okay, we have a planar convex lens which is placed on a glass plate, and this point P where the glass plate and the planar convex lens are in contact. Okay, so in order to derive the equation, we are not deriving the equation for the path difference. So we are trying to derive the equation for the constructive as well as destructive interference. Also, we are deriving the equation for the we have a number of rings, right? So we are trying to find the equation for the radius of the dark ring. Okay, that's what we are going to do. So here you can see I told you APB is a planar convex lens. So you can assume that suppose we have a sphere, that planar convex lens can be a part of the sphere. That is, I have represented two-dimensionally. I have a circle with the center O, and this planar convex lens APB is a part of the circle. Okay, I have a circle, center O. This planar convex lens APB is a part of the circle. With this concept, I am going to derive the equation for the diameter of the dark. Okay. So here I'm telling you this APB is my planar convex lens and XY is my lens, and this APB is a part of a circle at center O. Okay, then I hope you all know the definition of radius of curvature. So this distance, this radial distance is representing the radius of curvature R. Okay, this OA, that is O is the center of the circle. Okay, O is the center of the circle, and A is a point on the circle. This is OA, which is a radial distance, which is representing the radius of curvature of the lens. Okay, and this I told you this is a planar convex lens. APB is a planar convex lens, and this P is a point of contact. Okay, as we are moving away from P, you can see the thickness of the air film is gradually increasing. Okay, so corresponding to thickness, the center will be getting a dark spot corresponding to this zero thickness, and you can see there is a formation of rings. Okay, so corresponding to this maximum thickness Tn, I am getting my nth dark ring. Okay, corresponding to the maximum thickness of the air film, which is I have represented as Tn. Okay, this one, I am getting my nth dark ring. This is my nth dark ring. So from the center spot to this particular, this is Rn. That's what I have represented here. Okay, this is my center spot. So I'm representing this is PQ, this is Q. I'm representing this is Q. So AQ, which is the radius of the nth dark ring, corresponding to that I have the thickness Tn. Okay, so this Tn, which is the thickness of the air film, Tn is the thickness of the air film, correspond to the nth dark ring. Okay, which is correspond to the nth dark ring. So I hope you understand. That is APB is my planar convex lens curved surface. XY is my glass plate. Okay, this APB is a part of the circle with a center O. And this OA, which is the radius of the curvature of the lens, and this AQ, that is that nth dark ring. So AQ is the radius of the nth dark ring. Corresponding to the nth dark ring, I have my maximum thickness Tn. Okay, that is Tn is the thickness of the air film. So here you can see this. Suppose this is T1, this is T2, this is T3, like that. The maximum thickness of the air film is Tn. Okay, so that is my initial assumptions. With that, I am going to derive the condition for the constructive as well as destructive interference. For that, I have the equation. You don't need to derive the equation of the path difference. The equation for the path difference is delta is equal to 2 mu t cos r plus theta plus lambda by 2. Okay, 2 mu t cos r plus theta plus lambda by 2. Now let me tell you what are these terms. Okay, this is our picture. Okay, so mu obviously what will be, so here in this gap it will be filled with air, right? So the air refractive index is mu. Air refractive index is mu. Suppose instead of air we are filling something else, we will be getting the particular value of mu. So here this thing is filled with air, so we have the mu, which is the refractive index of air. Okay. Now T I told you that the center spot, this AP, this P, the center spot is 0 and it is gradually increasing. The thickness of the air film is gradually increasing. So T is a varying quantity. Initially it was 0, then it became T1, T2, T3, etc. The maximum thickness is represented as Ts. Okay, that is T, which is representing the thickness of the air film. Okay, the T is the thickness of the air film. Now I have cos r plus theta here. Okay, r obviously you know the angle of refraction. Theta, as in the case of air wedge, you already noticed this, right? So here there is an angle theta around this point P. There is an angle theta. So in the case of air wedge, between the glass plate there was an angle theta. Similarly, between this convex lens and the glass plate there is angle theta. That is the this angle theta. Now r I told you. Now plus lambda by 2. So this is the general equation, plus lambda by 2. Reflection happening on the surface of the denser medium. That's why this plus lambda by 2 is. So this is the general equation. This is given. You don't need to derive this. The equation is delta is equal to 2 mu t cos r plus theta plus lambda by 2. Okay. So generally this theta value will be very small. So we used to take delta is equal to 2 mu cos r plus lambda by 2. That is the general equation. Theta is a very small angle. As I told you, it will be less than 10 minutes. And for normal incidence, again there will be some changes, right? So this thing, for normal incidence, cos r is equal to 1. So this experiment is conducted in this condition for normal incidence. So again the delta become delta equal to 2 mu t plus lambda by 2. So this is the final equation that we got. Delta is equal to 2 mu t plus lambda by 2. Now let me tell you theoretically why that center spot is dark. I told you always the center spot is dark and it is gradually increasing radius. We will get alternate dark and bright rays. So why the center spot is dark? So here you can see. Okay, here you can see the equation for the path difference is 2 mu t plus lambda by 2. Okay. So in the case when thickness is equal to 0, that means at this point P, the thickness of the air film is 0. So here we have the equation that is 2 mu t plus lambda by 2 equal to delta. Substituting this particular condition, that is t equal to 0, here we will get delta equal to lambda by 2. And I want you to recollect that equation. While deriving the superposition principle, I told you that delta equal to lambda by 2, this thing is the condition for the destructive interference or darkness. Okay, that's why the center spot is always appears to be dark, and this is the physical explanation for why the center spot is appears to be dark. Okay, and there used to be a question from this particular point. Okay, yeah, I think in 2 or more university question paper this question was there. So I want you to remember this is our equation. This is our equation, delta equal to 2 mu t cos r plus theta plus lambda by 2. When theta is very small, because theta will be always very small, so the equation can be rewritten like this, delta equal to 2 mu t cos r plus lambda by 2. So here for normal incidence, cos r is equal to 1. Then for the equation reduces to 2 mu t plus lambda by 2. So in the case of this particular point of contact P, thickness of the air film is 0. Substituting that here, we will get delta equal to lambda by 2. That's why the center spot appears to be dark. Okay. Now we are going to derive the equation for the dark ring. Okay, equation for the destructive interference, because we are conducting the experiment using the equation for the dark ring. So I am just concentrating on the destructive interference. We are going to derive the equation for the destructive interference. Okay, so we have equation delta equal to 2 mu t plus lambda by 2 from superposition principle. Delta equal to 2n minus 1 lambda by 2 is the condition for destructive interference. Now we are going to equate these two. So we will get 2 mu t plus lambda by 2 equal to 2n minus 1 lambda by 2. That is 2 mu t equal to 2n minus 1. So this equation becomes 2 mu t is equal to 2n minus 1. When this comes to the side, minus 1 lambda by 2, which is equal to 2n minus 2 lambda by 2. Okay, so this cancels, so we will get 2 mu t is equal to n minus 1 lambda. Okay, so our n was starting from 1, 2, 3, etc. So we will get, when n equal to 1, 1 minus 1 lambda. So instead of this, we can write 2 mu t is equal to n lambda, where n starting from 0, 1, 2, etc. Okay, so this is the equation. 2 mu t is equal to n lambda is the condition for the destructive interference or dark. Okay,